So let's remember, so like x follows binomial n comma p. For example, suppose x follows binomial 10 comma 0.3. So if we remember our binomial correctly, then this is something like saying there's a coin for which probability of heads is 0.3, that is 30%. And if you toss the coin 10 times, then let x be number of heads. So this is some way of thinking about binomial. Now, so like suppose we want to like look at what x looks like. I mean, to do that we actually have to find a coin, like speak with some physics lab people, so that the probability of heads for that is exactly 30%, and then toss it 10 times and all that. But I mean, we don't have to all do all that. So what we can do, we can run the experiment in a computer. So you will run some piece of code, some software, something that will, I mean, so like you will actually not toss any coins, but at the end of the code, the results you will get will be as if you have done that, as if you have taken a coin with probability of heads so and so, you have tossed it this many times, and this many heads you have. So it will be as if you have done it. So whenever we do some things like this, it's called simulation. I mean, you are like almost all of you are science students, so I think you know what simulation means. For example, suppose you are simulating the formation of solar system. So obviously you don't actually form a solar system, but on computer you input variables, the initial conditions, as much as you can, and you let it run. At the end you get the product, which kind of tells you, like, with all known knowledge about physics, if initial conditions are like this, then the end result will be like this under these laws of physics. But you do all this in a computer without, but you can see what will happen if the experiment is actually run. So that's kind of the idea behind simulation, running experiments in computers. So if we want to do this, for example, we can do it like this. So we can say r binom 1 comma 10 comma 0.3. So you get 4. That means you just now tossed a coin with probability of heads 0.3 10 times, and there were 4 heads. And let me do it again. And just now I tossed a coin with probability of heads 0.3 10 times, and I got only 2 heads. So, oh, by the way, let me do something like this. So what just now happened is, I took a coin with probability of heads 0.3, and I tossed it 10 times, and I got 1 head out of 10. Then again I tossed it 10 times. I got 4 heads. Again I tossed it 10 times. I got 5 heads. And again I tossed it, I got some heads, and again I tossed it, I got some number of heads. So basically you just select, I mean you just got 5 variables. So the 5 here means you are getting 5 values, or 5 simulated values from the distribution of 10, 0.3, binomial 10, 0.3. So this is like, in probability terms, it's like there is some distribution, like f, some fx. X has PMF or PDF fx, and you are simulating n times, like, so that kind of means that you are getting like n values, x1, x2, dot dot dot, xn, such that if you actually have done a real world experiment where there is a real x which actually follows this PMF or PDF, and you run it n times, then for the first time this is the guy, second time this is the guy, dot dot, nth time this is the guy. Obviously we realize all these things are like random, but I mean it's random before you start the experiment, but once you carry out the experiment you get actual values. So before I'll press enter, I don't know what values are gonna come. So the 5 values that I'm gonna get just now are random to me. The 5 values that I'll just after pressing enter I'll get is random to me. But once I see them, they are no longer random. So we just did simulation. The original distribution was binomial 10, 0.3. From that distribution I simulated 5 values, and they are just like this. So we just did the R binom function. Now let me do 2 other. One is D binom. The other one is P binom. So what D binom does is, suppose D binom 3, 10, 0.3. Okay, so what this means is x follows binomial 10, 0.3. Suppose I want to find probability x equal to 3, then I'll just say this is D binom 3, 10, 0.3. If I want to find probability x equal to suppose 8, I'll do D binom 8, 10, 0.3. I mean, let's actually do that. So, and that's the probability. You can actually like take out your calculator and put in the formula that I told you. Like the formula was n choose x, p to the power x, 1 minus p to the power n minus x. Basically d binom is doing this formula, so you can actually look it up. I mean, obviously you expect that if I put instead of 8 11, this probability should be 0, because binomial only runs between 0 to n, that means 0 to 10, and it's 0. Now p binom is so what we learned is d binom is just the PMF, and p binom will just be the CDF. That means suppose p binom 5, 10, 0.3 is probability x less than equal to 5. That's it. So in that case, that's like probability x equal to 0 plus probability x equal to 1 plus ... probability x equal to 5. And yeah, I mean, let's do this. So p binom 5, 10, 0.3, which is this guy, and let me do another thing. So d binom 5, 10, okay. So you're looking at 6 numbers. So starts for 0, 1, 2, 3, 4, 5. So this probability x equal to 0, probability x equal to 1, probability x equal to 2, x equal to 3, x equal to 4, x equal to 5. And obviously we know that if we add these values, we should get the p binom. And let me try that. So I'll say sum of these numbers, and we get the exact values. Yes. So that's it. P binom, as I said, gives you the CDF, and d binom gives you the PMF. So now let me make general statements. The general statements are, this kind of thing happens all the time. So for example, for R, I'm sorry. Okay, so this is the one, this is the page. Actually, let me copy and paste the link. Okay, so look, this has many distributions we have learned and more. So it has beta distribution, binomial distribution, it has gamma distribution, obviously it has normal, Poisson, uniform, and I mean all these distributions are like very, very basic. None of these are like unheard of or something. So these are very basic distributions. I'm sad that we couldn't cover all of them, but we'll do like some of them more in the next few lectures. So let's take D unif. So once again, so look at the general scheme. So so R blah blah blah, like suppose X, Y, Z something, and with appropriate parameters, generally the first parameter is number of variables you want, and then the rest of the parameters. This R is used for simulation from XYZ. The D generally gives you the PDF or the PMF of the distribution XYZ, and the P XYZ gives you the CDF. So that's the general scheme. For example, R unif will simulate uniform random variables. So as usual, okay, sorry, let me copy these values a little bit for reference. I mean, I'm kind of copying and pasting bits and pieces of code. It's not coherent in themselves, but combined with the video, this should be like, I mean, a good track of what went on. So for example, if I do R unif 15 comma 4 comma 8, this is basically uniform 4 comma 8. So 15 comma 4 comma 8. So the distribution is uniform 4 comma 8. So we remember it starts from 4, ends at 8, and like as density fx equals 1 by 8 minus 4, that is 1 by 4, if x lies between 8 and 4. From this PDF, this is a PDF. From this PDF, it generates 15 values. How does it do that? Don't worry. But it does. So once again, these 15 values are now, right now, they are random to me. But once I press the button, I'll actually see some values. And when I see values, those values are not random right now. Now they're not random. I've already seen them. So this is like a common thing in statistics. Once you see the values after experiment, those values are not called random. So yeah, these are values between 4 and 8. Obviously, it cannot be outside as we expect, and there are 15 of them. Yeah, I have nothing more to say actually. Oh, by the way, so if we do D unif, that means we want to find out the PDF. We know the PDF is already, we know it's 1 by 4, so 0.25. So suppose we want to find the PDF at 4.3, which lies between 4 and 8. Remember, the order in which I write these things is like important. Like first I write the value I want, then the rest of the parameters. I cannot write 4 comma 4.3 comma 8. So this ordering is important. I know this should be 0.25. Okay. Also suppose I do P unif, and let's make this guy 5. So probability x less than equal to 5, which is 5 minus 4 by 8 minus 4. So 5 minus 4 is 1, 8 minus 4 is 4, so 1 by 4 is, it should be 0.25. Actually that's not sexy. Let's take 6. So 6 minus 4 is 2, 8 minus 4 is 4, so 2 by 4 is half. So this guy should be half, and it is. So once again, P unif gives you the CDF. So that's the old scheme. P something gives you the CDF, D something gives you the PDF or PMF depending on the case, and R something gives you the simulation, like it simulates. Usually I can talk more about this scheme, that usually when like writing R something something, the first value is like n. I mean, I should not call n because we use n for, I mean the first thing that we write is number of values you want, and then the parameters, and these parameters obviously depend on what the distribution XYZ is. For example, for uniform it needs lower to upper, for binomial it needs n and p and all that. And for dxyz, the first is like the value x and then the parameters. So this value x is PDF at x or PMF at x, and we have p xyz, once again x, and once again parameters, and we know this is the CDF at x. So this guy gives you probability x less than equal to little x. This guy gives you either probability x equal to x, which is the PMF, or it gives you fxx, which is the PDF, and this is like simulating this many values. So that's the scheme, and just take a look at the distributions page. I'm sorry. All the distributions you need, for example, Poisson is here, D Poisson, P Poisson, R Poisson. So, and gamma, I want to mention that the way we write gamma is like, for us, what's gamma, alpha comma beta, it's like alpha is the shape, and let me check, alpha is the shape, and yeah, and we should write scale, like I mean suppose, what I'm trying to say is, suppose I want gamma alpha equal to 3, beta equal to 5, and so suppose I want like 20 variables from that. So I will write R gamma, 20 variables, and then the parameters are shape equal to 3 and scale equal to 5. There is something also called rate. Rate is 1 by shape, and rate is 1 by scale, and scale is 1 by rate. Don't worry about that. Just follow this. Like if you want alpha, beta, so shape is alpha and scale is beta. That's all. And everything is same as before. Yeah, that's all for now. The final thing I want to say about the homework is, you can consult me anytime. you can consult me anytime you want. So this is like an ongoing process. Yeah, so good luck.